we're building the components that regulate the circulation, right? So last time, what we just talked about was autoregulation of the tissues and humoral control, right? Vasodilation, vasoconstriction. We also talked a little bit about how long-term changes to flow and pressure affect vessels. All right, so this talk is really connecting what we talked about in autonomic nervous system, all right, to what we've been talking about in the cardiovascular system. So that's the connection point here. The nervous system's regulation of circulation takes place through the sympathetic nervous system primarily, all right? Parasympathetic plays a role in heart rate, but the rest of it is all sympathetic, okay? So there's our objectives. So, refresher on the autonomic nervous system, right? Sympathetic nervous system, thoracolumbar origin, okay, so middle of the spinal cord, here and here, all right? The sympathetic division has a much more robust nerve supply to the body than the parasympathetic does. Sympathetic fibers go everywhere because of that statement. Supplies nerve fibers to all vessels. So because we have vessels everywhere, and the sympathetic nervous system supplies all vessels, it means we have sympathetic nervous system supply everywhere, right? So that's here, right? We have sympathetic stimulation of arteries, arterioles, and venules, and veins. So the whole kit and caboodle. The parasympathetic system, all we have really is connection to the heart, right? So our dashed line there shows us our vagus nerve connecting the brain, the parasympathetic, to the heart. There's no parasympathetic innervation to vessels except, and to black and white, right? Except for vessels to the gut. So because the parasympathetic is the rest and digest system, it can cause vasodilation of the GI tract vessels, right? So it's a rare exception. Okay, control center, brain. There's a vasomotor center in the brain stem. Okay, this isn't a neuroanatomy class, so we're not going to get into the wheres and hows, but there is a vasomotor system in the brain. There's a vasoconstrictor area, there's a vasodilator area, and then there's a cardioinhibitory area. That connection, or that vasomotor low-level unconscious connection, has connections up into the cortex and the mesencephalon. So ascending, so here's our vasomotor center. We have ascending pathways, and then we also have descending pathways. So the vasomotor center sends signals up to the brain and is affected by signals coming down from the rest of the brain too. Remember, the hypothalamus is kind of the middle of it all. All right, so the hypothalamus is connecting our cerebral cortex, our experience of reality, for lack of a better term, with our vasomotor center and our autonomic nervous system that's keeping our homeostasis where it needs to be, right? Makes perfect sense, less so for human beings because, and it's easier to understand in animals how this system is supposed to work. The fight or flee is usually real if you're a squirrel, right? For us, a lot of times, it's not really a fight or flee scenario, but our body acts like it. It's really just, it's an exam, run away, but it doesn't work like that. But still, your blood pressure, as you know, will go up, your heart rate will go up. Why? Because the hypothalamus connects with the vasomotor center. And you think the test is an enemy, right? So you get your blood pressure all up because of it. Then the adrenal medulla, remember, I guess I don't have a picture of that, but the adrenal medulla works like a global sympathetic nervous system supply, right? Because it literally releases the sympathetic nervous system neurotransmitters into the blood, which are then carried everywhere. So refresher of the autonomic nervous system with a view specifically at the blood vessels. It covers a lot, right? The sympathetic innervates arteries, arterioles, venules, and veins. So all the areas. Okay, so what does it do? Well, the autonomic nervous system, sympathetic in particular, like we talked about in that section, both branches are on all the time. All right, so that means that the sympathetic nervous system is always on, it's never off. So it can increase its tone, its output, its activity level, or it can decrease those things. So the stimulation that the sympathetic nervous system is creating all the time gives us what's called vasomotor tone. All right, and the story goes a little bit like this. Okay, so here's our x-axis is time. This is pressure on the y-axis. Okay, so at this time we're seeing blood pressure of right around 100. Okay, in this tissue. Now, we anesthetize the spine. Why specifically the spine? That's where the sympathetic nervous system outflow comes from, right? The thoracolumbar area, so the spine. So we're going to put the spine to sleep. When we put the spine to sleep, we're going to put the sympathetic nervous system to sleep. So what do we see? We see a drop in pressure. Why? We have turned down the vasoconstriction. The sympathetic nervous system, its tone is on all the time, constricting a little all the time. If we put it to sleep, it relaxes, and we get vasodilation, a decrease in pressure. All right, so this is proof that the sympathetic nervous system was on right here, right? Because when we turned it off, we saw an effect. So it must have been off. Okay, then the second part is we can see that norepinephrine, the primary neurotransmitter of the sympathetic nervous system, can make the same response that the sympathetic was doing at the beginning. So even when the spine is asleep, if we give an injection of norepi, we see an increase in pressure. Why? Because we've made a fake sympathetic nervous system, right? We're releasing its neurotransmitter into the body responds in the same way. So vasomotor tone, the idea here is we always have a tone. When the sympathetic nervous system reduces its output, pressure goes down. When it increases its output, pressure goes up. But it's always present. Now, it is also true, patients under anesthesia, they lose their blood pressure. That's also true. Now, they account for this. If you ever had surgery, one of the first things they do when they meet you is put an IV in your arm and start fluids. Right? It's because they know perfectly well that once you go under, your blood pressure is going to drop. So they want to make sure that you have plenty of plasma volume, okay, so that you can tolerate the reduction in sympathetic nervous system outflow. The other thing they will sometimes do in critically ill patients is they'll plan for this. Like they'll start an epi drip before anesthesia so that they can maintain the vasomotor tone. Okay. So baseline tone means we can turn it up or we can turn it down. We could do a very similar experiment with the heart rate and we would see the same thing, right? If we put the sympathetic nervous system to sleep, the heart rate will drop, which means it's on all the time, increasing it, right? Remember the balance? It's the balance of the two systems.